Okay, so let's go ahead and run through these. So on the board there, we have for the handout that I gave, there are a total of 10 area formulas that you need to be familiar with. Now, as far as what are you given on the FSA when it comes to formulas at the end of the year, you're not given a whole lot. So you do have to know most of these formulas. Again, they won't ask you specific just area questions on the FSA, but they use these formulas within our three-dimensional solids. So it's important that we know the formulas, because then when we get to solving for, say, volume of a three-dimensional figure, you first have to figure out the area of the base. So you're going to have to use one of these formulas first before you can do anything else with the three-dimensional solid. So on here, we have given a triangle given the base and height. So there are two different formulas that we use for a triangle. The first one is one that hopefully everybody is familiar with, and it is using the base and height. So on this diagram here, I have for this triangle, this could act as the base of the triangle. Or in this triangle, I could use this as the base. Now, base does not necessarily mean on bottom, all right? So it is possible that we could turn our figure as well. Now, for each of these, if we were to do that piece as our base, the height is the distance from the base to the opposite vertex. Probably sounds familiar because it's kind of the same idea as altitude earlier in the year. So if I was to draw the altitude in here, this segment is our altitude. The length of that segment is what we refer to as the height. Same thing in this triangle. In order to draw the altitude in this one, I had to extend the base and then draw the height down to that. Again, it is a perpendicular distance from the base to the opposite vertex. Anytime you think about height and base, the base and height should always be perpendicular to each other. So now, does anybody know the formula for area of a triangle? All right, so area equals base times height is going to be our formula for a rectangle, which is the one right below this. So I'm going to go ahead and write that down real quick. Area equals base times height. So on the rectangle down here, I can label this bottom piece as my base. And then this will be my height. But now a triangle, yeah, so we can say this a couple different ways. Some of you guys might be familiar with it as 1/2 base times height, or a lot of teachers like to use it as base times height over 2. Either one of those is acceptable. It's the same formula. It doesn't matter if you multiply by 1/2 or divide by 2. It's the same thing. Just remember, a triangle is essentially half of a rectangle. So again, don't forget to multiply by 1/2 or divide by 2 when finding the area of a triangle. Now, a lot of things are based off of that formula for base times height. So a rectangle is base times height. You might also know it as length times width. That's fine too. In geometry, we normally use base and height instead of length and width. Also, when we write these formulas, notice I'm using lowercase letters. All single dimensional measurements for lengths use lowercase letters. If we are talking about a three-dimensional figure, we start using uppercase letters for a couple of those dimensions. But for a two-dimensional figure, any single dimensional measurement is usually given as a lowercase letter for a length. All right. Now, on the next one, parallelogram. Well, a rectangle fell into the category of parallelogram before, right? When we did our quadrilaterals, a rectangle was a type of parallelogram. So guess what our formula is for a parallelogram? Same thing, base times height. Because if we were to look at a parallelogram, and you don't have to draw this extra figure I'm going to draw in here. If I was to draw a parallelogram and think about cutting off this side of it, right? And take that triangle, cut it off, and I'm going to take it and I'm going to move it over here. Well, now what outline would I have for this figure? That would now be a rectangle, right? It's the same thing. That triangle would fit into the other side, complete the rectangle. And again, we end up with base times height. Now, again, it is a perpendicular distance. So I do need to make sure that I'm using not the side of the parallelogram, but the perpendicular distance between the other sides. So if I call this the base, then that's the height. All right, a rhombus. Well, again, a rhombus fell into what category? Parallelogram. All right, so we do have base times height, which would work here, but they don't always give me base and height when finding area for a rhombus. So there's another formula that I can use. So I have base and height, just like the other one. But now on this other diagram, I'm going to draw something else. We have diagonals that we can draw into a rhombus. And there's some special properties that we learned about the diagonals in different figures. And for our rhombus, what was special about the diagonals? Anybody remember? What's special about those two diagonals? How do they intersect? What you got back there? You said half? Is that okay? So in a parallelogram, all diagonals do bisect each other, but in a rhombus, there's something a little more specific. And it has to do with the angle that they meet at. These two diagonals are going to be what? They're going to be right angles. Are they going to be perpendicular? So in this figure, since these are perpendicular, notice if I was to just talk about half of this figure now, forget that this other half is here, what shape would this be? A triangle. So I can essentially use my formula for area of a triangle here as well, but instead of calling it base and height, it's going to be the length of the first diagonal and the second diagonal plugged in for where base and height normally would be. So it's going to be 1/2 diagonal 1 times diagonal 2. All right. So that's the first 4. Any questions there so far? Now, for our next shape, we do have another repeat. Let me save these. All right. So now a kite. A kite, we do have another formula is a repeat from something we've already done. Here, I'm going to draw in 2 diagonals. Yes. Yeah. And again, these diagonals meet so that they are perpendicular. So we have the area of the kite is 1/2 diagonal 1 times diagonal 2, just like that second formula for our rhombus. Again, when I say diagonal 1, it's that entire length all the way across, and then the other length all the way across the other side. Now again, it's that whole length of that diagonal. I didn't label the other one like that just because I didn't have room. Again, it's the entire length of those diagonals. All right, trapezoid. Anybody want to take a guess as to our formula for a trapezoid? So what parts do we have so far in a trapezoid? So on here, what's our base in our trapezoid? Yeah, B1, B2. All right, so let me label that B1, B2. So we have 2 bases in a trapezoid. we have a height? Yeah, our height is going to be the distance between those bases. And again, it's the perpendicular distance between those bases. Height is always a perpendicular length compared to the base. So those are the three pieces we need. What's our formula look like? Yeah, no, you're doing good. All right. So different teachers probably write this different ways. I always write it as 1/2 base 1 plus base 2, and then times the height. Essentially what you're doing here is you're taking an average of the two bases and then multiplying it by the height, because in a rectangle, right, we would have just base times height. Well, this one we have two different lengths of our bases. So if I was to take this triangle here and move it over here to the other side, the overall length of each of the bases at that point would be exactly in the middle of the two that we had. So that's going to be the average of the two bases times the height. Now, if you already know any of these formulas in different setups, I'm fine with that. Again, this is the way that I will always write the formula when we use it in class. But if you're okay with it in a different setup, again, I'm not trying to change what you've been taught before. So I'm going to show you a couple other versions of this. You do not have to write any of these other versions down. But some teachers teach it that way, which that way kind of matches what you were telling me originally with my equation, b1 plus b2 divided by 2, and then times height. Other teachers mix it up as to what comes first. So some people like to put the h first, which I don't think this one makes any sense. But that's fine too. Again, I will always use the same format whenever I do my equations. So I'll always do mine this way. But I do understand if you've learned them before, you might know it a different way. And if you want to use the old one that you've used a million other times, that's fine. Now, the next one is going to be new. Actually, the next two are going to be new to us, because the next one uses a little bit of trig. I'm going to label this triangle as triangle A, B, C. Now, when we label the corners with capital letters, the sides across them, we should label with the same letters, but they're lowercase value. So we have side A, this will be side B, this will be side C. The formula for this one, it's going to be 1/2 AB sine of C. So notice 1/2 lowercase ab sine of uppercase C. What this is saying is we're taking the two sides that are adjacent to each other, all right, and then the sine of the angle that's between them. Now, this formula is actually based off of our regular equation, but normally we have to find our height, right? Well, since we have these trig properties from before, we can use trig to find the height. And that's all this is doing. This is essentially saying, all right, if A was our base, B times sine of C would end up giving us what the height is. So it's just replacing those values and writing it in a way that will allow us to solve for the area by using trig. Again, this formula, it can be rewritten in many ways. I'll normally always write it in this format. However, if you want to switch the values around, you could do any combination of the two lowercase letters and then the angle that's between them. So you always use all three letters, two lowercases and the one uppercase when doing the sign. So I could also say 1/2 BC sine of A, or I could also say 1/2 AC sine of B. Same equation, Same outcome. It's two sides that are adjacent with the angle that's in the middle. So again, the setup doesn't really matter that much. It's the same thing each time. All right. The regular polygon. For a regular polygon, there are some parts that we have not gone over before that we need to talk about. So there are two equations, essentially, that we are going to use here. It is 1/2 A and a capital P, or we could also say the area is equal to 1/2 lowercase a, lowercase s, lowercase n. Now, what do these different parts stand for? So we have some letters. I'm going to write down what they stand for. So we have an A, we have an S, we have an N, and we had a capital P, right? Does anybody know what the P stands for? Because we've used the capital P before. Perimeter. All right. We've used N before. Does anybody know what N stands for in this one? It'll be the number of sides. So however many sides there are, in this shape, we have a hexagon, so it'd be 6. S is going to be the length of a side. Again, since we're talking about a regular polygon, what's true about all the side lengths? They're all equal. So again, that's why we're able to just say S, because S is the length of a side. And then A, this one's a brand new word that you haven't heard before. Apothem. It's spelled like apothem, but again, it's said apothem. Now, what is the apothem? So that's the only one that you don't know here. The apothem is kind of like a radius, but it is going to the side of our figure. So it's this perpendicular length from the center point of our polygon to the side of our polygon. So that's going to be our apothem. So on here, labeling important pieces, I have my apothem. I have the length of a side. Those are things that I could label here. Now, I had two different equations. I had either 1/2 AP or 1/2 ASN. Well, P, how would you find perimeter of a regular polygon? If I knew the length of one side, I know the length of one side. I know how many sides. They're all the same. So just multiply that length by the number of sides. And that's why really these are the same formula. S times N gives us perimeter. So they just replaced S and N with P. So again, either of those work. All right, going on to, does anybody need anything else there before I move on? All right, going on to the next page then. All right, circles. There are two formulas that we need to know for a circle when it comes to area. So the first one, this one probably everybody knows. Hopefully. Area of a circle. We've done this one many times. You learned this one in elementary school. Area of a circle. So the first, one of the pi times the radius squared. Sure. I usually say it's pi r squared. Yeah, pi r squared, or pi times the radius squared. Either way you want to say that, that's our equation for a circle. pi r squared. And there's the old horrible math joke. Pi's aren't squared, they're round. Yeah, it's horrible. Pi r squared. Yeah. Anyway, sector. All right. Oh, actually, before we go there, let's label this figure. So on this circle, the one piece you need to know is, of course, our radius. Now, what is a sector? Anybody know? Because we have not talked about that yet this year. It has something to do with a circle, though. Anybody know what a sector is? If I said a sector of a circle, what do you think? What do you think? What do you think a sector is? It's not a segment. So if you think of a circle like a pizza, right? It's like a piece. It's like a slice. So that's the drawing here. So this is a sector. Now, when you are doing your formula for area of a sector, it is just like what we did pretty much for our arc length formula. We're going to take the fraction of the circle that we're using. So how many degrees are in a circle? 360. So we have the measure of either, again, you can either say the arc or the central angle. Doesn't matter which one you call it, because again, that's the same thing. But the measure over 360 times, now when we did area, when we did our length of a sector, or sorry, length of an arc, we used our formula for circumference. Here, we're multiplying it by the area of a circle. We're doing area of a sector. So pi r squared. So again, the measure of the central angle or the arc that we're using over 360 times pi r squared. So those are all the formulas that we need to know and be familiar with when it comes to area. I know there's a lot of them, and that's why I'm having you write all these on one sheet. Try to keep this in a good place in your notebook, somewhere handy, because you will probably want to refer back to this for like the next 5 weeks. Because everything that we do with three-dimensional shapes, whether we're doing surface area or volume or whatever we're doing with three-dimensional shapes, a lot of them refer back to these formulas, because if I want to find the area of one face or the area of the base or the volume of the figure, I have to do one of these area formulas first before I can do anything else. So we are going to use those formulas over the next few weeks. Now, I'm not assigning any other assignment today. I'll make a spot on Canvas for turning in these notes as an assignment. I guess I must not have posted or published the assignment yesterday, so I'll make sure I publish that here in a minute as well. But just make sure you get the notes turned in later today. And then tomorrow we'll start going through some examples and using some of these formulas. All right. So, save that one.